Okay, welcome. Good afternoon and welcome to the webinar hosted by the Canadian Institute for Cybersecurity at the University of New Brunswick. And today we are fortunate enough to have Mahdi Firoozjaei joining us. He's a research fellow, postdoc research fellow at the University of New Brunswick. And today he's going to talk about secure and reliable messaging system under network disruption.
Good afternoon. My name is Mahdi. I'm a postdoc fellow in the CIC. Today is talking about the instant messaging, the secure instant messaging under network disruption. In this presentation, I will present our introduced model O2TR. And information about the instant messaging, briefing information, OTR security protocol, limitation of OTR, and our suggestion to cope with the problems. Evaluation and conclusion will be present by my slides. I think it's a silly question if I ask you if you use any instant messenger in your system, in your mobile, in your cell, in your PC or not. KakaoTalk, Skype, and WeChat or WhatsApp are some normal application you are using. And interestingly, last year, totally 28.2 trillion internet traffic belonged to the instant messengers or IM. In this photo, you can see that the most popular application for instant messaging for this year, the number of active users in the months. The most famous application is WhatsApp with about 1,500 million users in months. And if you ask me what is the reason for the popularity of this application, we can mention some advantage for them. Usually, they are very easy to use, real-time responding, and use. There are available a lot of services, group chatting, video sharing, voice sharing, banking, and etc. This application are very desirable for normal activity for internet applications. But unfortunately, there are some issues related to the IM services. Usually, IM services are vulnerable about some security threats such as impersonation, eavesdropping, or information leakage. Based on this, there are some security solutions with the approach to cope with these issues. Normally, two kinds of the solutions have been provided: centralized and non-centralized. In the centralized solution, a third party or an independent center should provide some security features, for example, key management or users authentication centers, or maybe the messaging server provide both service of messaging service and also the security services. In the second solution, the users they try to provide some end-to-end security by themselves. In this case, we don't need any third party, or we shouldn't trust to the service provider. If we want to have a brief view about the centralized solution, in some applications like Skype or Telegram or KakaoTalk, the service provider, the messaging service provider, also provide the credential management, key management, or etc. In this case, if you want to provide a secure session or provide any encryption, the server share the keys with the client. Based on these keys, the client encrypt and send the message to the server, and it will be delivered to the receiver. But in this case, you should trust the IM service provider, because every key or every management should be provided by the service provider. So what would happen if we are facing with untrusted service provider, any legal or illegal surveillance or message retention? So in this case, data manipulation, confidentiality and integrity compromising, or privacy violation can be happen in this solution. In the second solution of the centralized, usually used by the WhatsApp or Signal systems. In this case, we should use a third party, a separated server for credential management. In this case, this separated server provide the key management and authentication services to client. So if you want to send your message, if you want to provide a secure session and send the message securely, the third party share the key to the client. Based on these keys and application, the client encrypt and send their message through the messaging service provider. So these two servers are separated, completely isolated, and every key management and encryption progress should be performed by the third party securely. Signal is a very famous protocol, or in previously it was called TechSecure. In the TechSecure, the security core of Signal is the security core of the WhatsApp application. Provide perfect forward secrecy, secure conversation by an authenticated encrypted scheme. But as I mentioned, in this case, same as the previous one, you should trust the third party, you should trust the Signal server. It has been shown that it's completely secure and provide a lot of security features, but there are some usability issues. For example, what would happen if this third party reject to provide renewed keys and use the keys separately or severally, or if the message is or if you try to fetch the receiver's information, the server hand you the real information. Yeah, in this case, you should trust the third party. But the Signal has shown that it's completely secure. The third solution, or actually the second solution, is non-centralized solution. In the non-centralized solution, we don't need any separated server, we don't need any third party for credential management. Every keys, every security application should be performed by the client themselves. So they don't need any separated server. As you can see in this animation, the users handshake and try to change their key together, and based on this key handshaking, the message will be encrypted and sent to the receiver. So in this model, the service provider is only the center to provide the messaging application, not else receive the message and deliver to the destination. So the server doesn't have any authority rule or any rule in the credential management. OTR, off the record, or silent circle instant messaging protocol, SCIMP, are two famous models for security application for this. But please note that if you want to use OTR or SCIMP, we should install the plugin over the current messaging application. So if, for example, Pidgin or CryptoCat are the basic messaging application, in this case they don't provide any secure session. If you want to provide any secure session, we have to install OTR as a plugin over CryptoCat, and then we can run the secure session together. End-to-end security and perfect forward secrecy are services provided by this model of the security solution. Uh, OTR, as as I mentioned, OTR is a security protocol provide end-to-end security. Usually, OTR provides four basic security features: authentication, encryption, deniability, and perfect forward secrecy. If we compare this protocol with the other IM application like Telegram or Skype, OTR provide very unique services, deniability and perfect forward secrecy. In the deniability, same as oral conversation, when you talk with any friend orally, in the next time that guy cannot prove that you did that you did say something at the past time, because it was not written and there is no proof that shows that you did something and or you said something. So in this case, the deniability in same as oral conversation, OTR provide the deniability in the IM applications. Perfect forward secrecy, same as the other solution in this case. If our current key is compromised, no message or no information in the past can be delivered, can be revealed, because we are using ephemeral key for every message, and every message security depends to the current key. So if the current key is compromised, the previous messages will be safe. To have a brief look on the OTR handshake process, if you note this figure, you can see that at the first in the first in the first in the first message exchanging, the two clients try to exchange their Diffie-Hellman key shares and then in the second step, the sender try to encrypt his Diffie-Hellman share sent to the receiver, and after verifying each other's secure channel will be performed. So at first they try to exchange their Diffie-Hellman key shares. By generating a share key, they try to verify each other's. Based on this verification, based on this authentication, they can provide a secure channel. In this secure channel, the the OTR parties try to start to exchange their messages. In the data exchange phase, you can see that in any the message packet, the sender suggests his or her next Diffie-Hellman share. So if you can see that in the message packet, the sender mentioned his suggestion for next Diffie-Hellman in this part, and the message will be encrypted by AES 128. In response, and also the packet is authenticated with MAC code. In response, the receiver will share his or her share key to the sender. To provide the deniability in any message exchanging, the authentication key, the MAC key for the previous messages will be revealed. As you can see in the KJ star, the previous key of the previous messages, any messages before the MAC key will be revealed here. So anyone can access these keys. So in this case, it cannot prove that it's not provable that who actually sent that message, because this message is publicly available for any guy. By sending the suggested Diffie-Hellman and receiving the suggested Diffie-Hellman for the next message, for the next message pair, they provide a chair key generation for this OTR session. So this chair of key generation is called OTR ratcheting. In the OTR ratcheting, key generation is pairwise and therefore encryption authentication is pairwise. So both sides should cooperate to generate the key, and therefore the authentication and the encryption will be pairwise between two sides. That was the brief introduction about the OTR and OTR handshake and data exchange. Let me go to the online messaging. What is the online messaging? If in any message exchanging, when you send a message to the receiver, if the receiver is online and also is in the chat room, the message immediately will be delivered to the client, to the receiver. So this kind of message is called online message. What would happen if the receiver is not online, or for example he or she left the chat room? In this case, when you send the message, this message will be retained, will be stay in the server side. This message is called offline message. Whenever in the future, whenever the receiver get online or entered again to the chat room, the message will be delivered to the client, to the receiver. But in the normal case, it's very normal when you send a message in the Skype to your friend, to your client, to your partner. In this case, anytime he or she get online or enter the chat room, the message will be delivered, and maybe today or tomorrow or next week, she or he can read the message. It's very normal. But what would happen if the message was encrypted in a secure session, and right now, because I left the chat room and at this time I don't have any key to decrypt the message? Please go back to the OTR ratcheting. As I mentioned, in the OTR ratcheting, we are using ephemeral keys. So for any message, any encrypted message, we are using ephemeral key, one-time use key. And also, the key generation is chained together. So the current key is chained to the previous one, and also will be chained to the next one key. So any key is chained together. And the encryption and authentication are pairwise. Whenever you receive an offline message, because that message was encrypted in the previous session, actually is not readable by the receiver. So the OTR is only usable in the synchronous communication. In the synchronous communication, both sides of the communication should be online simultaneously. So OTR is not applicable in the offline message. As an example, you can see that this example is about the OTR session performed in the Gajim messaging application. The receiver received a message. This message actually was encrypted in the secure session, but now the receiver is not already in the secure session, so the message is not readable. It's not the receiver is not able to decrypt the message. In the normal case, usually we will face this problem, and easily we can ask the sender, please send your message again, and resending very easily, very immediately. Yeah, it's normal. But what would happen if you're talking about any emergency or any unusual case, for example, in the earthquake or flooding or any natural event? In the natural event or in any emergency case, each message may be worth the life or death of the victim. So we shouldn't ignore any message in the emergency case. For example, in the last year in the Iran in Kermanshah, we had a very fatal earthquake, and so in this case, you can see that you cannot predict the next event of the natural disaster. So any message in the emergency case should be considered as a valuable of the victim's life. So in this case, if that message, that emergency request was encrypted by the OTR, at this time is not It's not readable, and also the victim is not able to send it again. To cope with this problem, we introduce OTR, offline OTR. In the offline OTR, we try to provide the privacy preserving for instant messaging clients in both cases of online or offline case. Uh, uh, our introduced model is a secure and reliable messaging systems under any network disruption condition. So if in any case the client gets offline intentionally or maybe by some natural or technical problems, the message will be in the safe side, and the next time it will be the receiver is able to decrypt the message. To evaluate the performance of our model, we implemented OTR on the Gajim system, launch of the XMPP Jabber platform. The basic idea of our model of OTR is that, as I mentioned, in any OTR packet, there is a part next Diffie-Hellman. In this case, the sender mentioned and suggests his or her next Diffie-Hellman share to the receiver. So in any step of the OTR message exchanging, the receiver knows that what is the next Diffie-Hellman share to be used. So in this case, the OTR parties know that what is the next Diffie-Hellman share of the other side of the OTR session. So we are using this idea in the OTR. In this figure, you can see that the basic module which we added to the OTR is shown here. Actually, OTR model consists of two new parts: OMD, or offline message detection, and also EKM, emergency key management. In any key generation, in any key messaging, a copy of the next Diffie-Hellman share is saved in the EKM part. So automatically in any message generation, in any key generation, a copy of the Diffie-Hellman share. Please note that Diffie-Hellman share, not the encryption or decryption key. The Diffie-Hellman share will be saved in the AKM. Whenever you receive an offline message, the OMD will detect if this message is an online message or is an offline message. If you receive an offline message, the normal key cannot be used, and we should refer to the AKM. So in this case, we extract the last Diffie-Hellman share suggested by the OTR party, and then generate the key for decryption. So the message will be decrypted and readable by the receiver. To implement our model, we use Gajim application as a basic instant messaging system. We use eJabber XMPP server implemented on Ubuntu 14.04 to provide the Jabber platform, and also we use OTR plugin. The OTR plugin available in the GitHub. We optimized this plugin and add our two models, OMD and EKM. So in this case, we updated OTR plugin and generated O2TR plugin and added to the Gajim application. In this figure, you can see that what would happen if we receive an offline message. If we receive an offline message, the OMD will detect this message is not online message, is an offline message. By this, in this case, OTR module will refer to the EKM to extract the previous Diffie-Hellman share, and based on this, we resume the private session. So in any network disruption or in any OTR interrupt in the private session, O2TR can resume the private session. So in any case, we can detect offline message and also retrieve any message, any offline messages. Our implementation shows that fortunately we could completely 100% successfully detect the offline message and decrypt the offline messages. The in OTR completely can resume the private session, and also we try to alert the sender that your private session has been resumed. So we recommend both sides to renew their session by generating a new development share key. For time processing, in this table you can see that incoming message, outgoing message, the comparison between OTR, the original OTR protocol, and also our introduced protocol OTR. As you can see in the incoming message, there is no comparable difference. 15 millisecond for OTR, 16 millisecond for OTR. But the main difference happened in the in the outgoing message. There is not the meaningful difference. It's about yeah, it's approximately the same. But for incoming message, yes, is about 1 millisecond difference. In the instant messaging, 1 millisecond is comparable. If I try to mention the reason of this difference, it's in that in the normal OTR, by receiving the message, any progress or any process shouldn't be performed to detect if this message is online or offline. By detecting any offline message, the message will be withdraw. But in our model, in the OTR, by receiving any offline message, we should refer to the local memory to fetch the previous defilement share and then generate the keys. The key generation referring to the local memory usually take 1 millisecond averagely. So in this case, our model in the incoming message processing, we will take some time. But the main advantage of the OTR is being able to handle offline message. As you can see in this table, OTR is not able to handle the offline message, but our model is able. But there is a difference between the time processing for offline message and incoming message. You can see that our OTR takes 2 times longer to processing the incoming message. Yeah, it's normal because, as I mentioned, referring to the local memory, generating the new key, and then encryption usually takes time. But by detecting and generating the first key for the next time, this time will be decreased. I think it's less than the normal processing time for incoming message, about 9 milliseconds. To resume the interrupted secure session, the private session, our model, the OTR model, has an advantage over the normal OTR protocol. As you can see in this figure, you can see that the averagely OTR takes 34% faster than the original OTR protocol to resume the private session. If you want to provide handshake by the OTR, in comparison to the private session resumption in the OTR, usually OTR provide faster resuming progress. So our model is 34% faster than the normal OTR. Is a very good advantage over the normal OTR protocol. So in the private session disconnection, OTR not only retrieves any offline message, but also resume the interrupted private session faster than the original OTR protocol. To analyze our model in the security view, as I mentioned, based on the OTR ratcheting, any key generation should be proved by the receiver. So, in the first step, the sender suggests his or her development next key. The receiver will acknowledge and that that introduce development key share, and in the next message pair, the new key will be used. So any key generation should be suggest, acknowledge, receive, send, acknowledge, receive. So in this case, uh, any key generation should be wait until receiving the acknowledgement from the receiver. What would happen if you have to send several messages before receiving any response? So in this case, you should encrypt your message several times with the same key, because any key generation needs the acknowledgement from the receiver. If you have to send, for example, 5, 10, or 50 message continuously before any receiving any response, so in this case, you should encrypt your message with the same key until receiving an acknowledge and generate the new key. So in this case, the maybe two-time pad problem happen. What is the two-time pad problem? In the block ciphering, if you use two different messages with the same key, maybe the two-time pad key problem happen. As you can see that in this case, the English alphabet has uh, it has proven that if you use the same key to encrypt two different messages, it can easily be detected because of the two-time pad problem. Based on to avoid the same problem in the block cipher encryption, it has been suggested that the upper bound for any block ciphering, same as AES 128, exactly for AES 128, the upper band is 2 power 64. It shows that you can use same key 2 power 64 times to encrypt. Exactly for AES 128, the upper band theoretically is 2 power 64. But actually, uh, the NIST recommend that for AES 128, if you are using block size of 128, it's better to use only the same key to encrypt 2 power 28 blocks, not longer. So they provide that only for 2 power 32 message. We can use the same key for encryption. But this is the actual upper bound for the AES 128. But actually, it's very huge number, and in our case, we can mention a smaller threshold. For example, in our model, we provide that if in any section, if you have to send several messages, we provided the threshold 1024. In this case, we can use the same key to encrypt 1024 different messages. It's I think for our model, it's very huge number. I think it's not normal to send, for example, if you want to send a message with any instant IM application, not more than 1,000 times. But actually, by assigning this threshold, we can provide a secure environment, safety environment for our application. To check to analyze the security of our model, we evaluate OTR with the Avispa security tools. And the result shows that in our implementation, the attackers try to detect the message text and also find the session ID. But eventually, Avispa shows that our model is completely secure against this kind of the attack. Actually, in the OTR, we didn't we didn't perform any change for OTR. OTR is a completely secure, provide the perfect for secrecy, and OTR is using the same progress, so it's secure. The main difference with the OTR is providing the capability to handle the offline message and provide the faster capability to resume the private session. So the evaluation of Avispa on the Spain animator indicate that our model is completely safe and for security views. By OTR protocol, we try to cope with the OTR limitation for asynchronous communication. In this case, we shouldn't impose any significant processing time to IM clients. And also we provide faster private session resuming 34 times faster than the original OTR protocol. And also we found that our model is secure against man in the middle attack, reply attack, and two-time path situation. Currently, we try to extend OTR model to OTR protocol to provide a completely secure communication system for emergency communication. In this case, we try to omit any handshake progress. In this case, immediately the victim can send his or her emergency request to the emergency secure center, and the emergency message will completely securely delivered to the trusted server. And we try to develop our model for no handshake communication. And thank you for your time and listening. It was my slide and presentation for OTR and secure message. I would be happy if there is any question or